Let's talk about nitriles. Nitriles we've mostly seen in a synthetic context as a product of an SN2 reaction between maybe some terminal bromide and cyanide, sodium cyanide. So why am I talking about nitriles along with esters and acid chlorides and all that? This doesn't look like a carboxylic acid derivative, right? Because all the other, for instance, if I compare this to an ester, right, this just looks different. But both of these have a carbon with 3 bonds to an electronegative atom. So this has 3 bonds to oxygen. This has 3 bonds to nitrogen. And so really all of the carboxylic acid derivatives that we've talked about so far, acid chlorides, anhydrides, esters, amides, they all fall under this category of carbon with 3 bonds to some electronegative atom, oxygen, nitrogen, chlorine, etc. So nitriles can undergo hydrolysis in the same ways that esters and amides can undergo hydrolysis, and essentially by the same mechanism. So let's go by acid first. What if I were to cook this in aqueous acid? Well, where is the most basic site in a nitrile? It's definitely going to be this nitrogen on the end, right? So now I have my protonated nitrile, and just like an ester or an amide, now this is a much better electrophile than that was. So by using acid catalysis, I'm making my electrophile more electrophilic so that some weak nucleophile, like water, anytime you see H3O+, assume that there's a little bit H3O+ and a lot of H2O, right? This is the solvent. So H2O is going to come in as my weak nucleophile. Those electrons go back to nitrogen. I end up with this after water attacks. Again, I'm not attacking with OH-, so this oxygen still has 2 OH bonds. And I have the CN double bond, which we haven't seen a whole lot. But we can imagine that nitrogen is still more basic than oxygen. So I'm very quickly going to establish an equilibrium between this intermediate and this intermediate. So this is kind of like the equilibrium between tetrahedral intermediates that we talked about earlier. And it's driven to the bottom because nitrogen is quite a bit more basic than oxygen. Now, here's a fun trick. Draw a resonance structure of this bottom intermediate. Go ahead, stop the video for a second, and see if you can draw the resonance structure of this intermediate. So here it is. This is a resonance structure of this. So these are the same things. So what looks weird over here looks more familiar over here. All this is a protonated amide. We saw this in our video about amide hydrolysis, right? So once this loses that acidic proton back to water, I end up with an amide. So I'm able to hydrolyze a nitrile to an amide in aqueous acid. So we just described how we can get from this nitrile to this amide by hydrolysis. If we remember that we can also hydrolyze amides to carboxylic acids, we can start to put these moves together a little bit, right? So I can start with a nitrile, cook in aqueous acid, probably boil it, get the amide. If I just keep that amide in the pot, keep cooking it with aqueous acid, I'm going to get carboxylic acid. So as a homework doer and test taker in this course, you might be very concerned about this, that how will I know whether it's going to stop at the amide or stop at the carboxylic acid? I think that in a homework question, I would accept either of these. If I were to ask you what happens when you cook a nitrile in aqueous acid, either of these could be a correct answer, for one thing. Secondly, the more interesting homework and test questions you'll have will be more like, how can I make stuff, right? This gives me the freedom. I can make either amides or carboxylic acids by starting with nitriles, which is pretty cool because I even know how to make nitriles. I can make nitriles by using alkyl bromides and doing an SN2 reaction. So now I've got a way to turn any alkyl bromide, if it's SN2 appropriate, right? Primary, maybe secondary, right? Primary bromide to nitrile to amide to carboxylic acid. Another thing we can do with nitriles that we mentioned earlier is we can reduce them to primary amines. All right, so catalytic hydrogenation works pretty well on nitriles. So nitriles are really, really useful synthetic intermediates. I can start with an alkyl bromide and get to 1, 2, 3, 4 different functional groups. And we'll actually learn later in the course how we can use this to functionalize the carbon next to the nitrile as well. So this is a nice sort of branching point when we think about building our synthetic web of different things that we can make from different things.